I wanted to show you my favorite proof in all of abstract algebra. I don't know what it is about this proof, but it always makes me smile. It's just such a little proof, but it's really interesting. So let me show you what I'm talking about. So here's the theorem. Let G be a group, and suppose we have two subgroups, N and K are subgroups such that, in fact, N is normal in G and K is normal in G. So they're both normal subgroups. And the intersection of N and K is trivial. Then the elements of N and K commute. That's an impressive result because it doesn't seem like we have anything, we don't have much information about N and K, but just out of this, because N and K are normal and the intersection is empty, then the elements commute. Commuting is a very strong condition on groups. So how does that work? So by the way, what I mean is i.e. for all N in N and for all K in K, we have that nk is equal to kn. Okay, so they commute. And here is the proof. The proof is very short, but it's really nice. So let's consider the element C, which is n times k, n inverse k inverse for n in n and k in k. And note that this element, which is again what we call a commutator, is the identity if and only if nk equals kn. Because if nk and inverse k inverse is the identity, then if I multiply in this equation on the right by k and then on the right by n, I get this equation. So an element, this element C will be the identity if and only if the elements commute. So let's prove that this element is the identity. And here's how I'm going to do it. So let's write again n, k, n inverse, k inverse. And notice that what is this? Since k is normal, so because k is normally in G and n is in G, that tells me that nkn inverse, so I'm going to put a parenthesis around this element here, nkn inverse has to be also in K. So this nkn inverse is in K times K inverse, this will be in K. Okay, so because if this is in K and this is in K, then the product will be also in K. So the upshot of this is that C, this commutator element, is in K. And similarly, I can rewrite my nk and inverse k inverse as follows. I'm going to put parentheses in here. And now notice that because n is normal in G and k is in G, these two things together tell me that k n inverse k inverse, that is also in n. Why? Well, first of all, n is in the normal subgroup. It is a subgroup, so n inverse is in the subgroup n. N is normal, so when I do conjugates, I land again in n. So this is in n, this is in n, and therefore this is in n. The upshot of those two things is that my commutator C, it is also in n. Thus, what I've proved is that C is in N intersect K, But remember that that was one of my assumptions, was that the intersection of the two groups was the identity. So this is the identity, and therefore C is the identity, and therefore nk equals kn, which is what I wanted to show, because since that was an arbitrary n and an arbitrary k, every element in the normal subgroups n and k commute. And that's it. That's the proof. And I think it's really cool that it's just a proof by parenthesis. You're just putting parentheses in the right place, and then the proof follows. So that's it. We are actually going to use this as part of the course that I'm teaching in abstract algebra to prove some other things, but I wanted to write this statement just as a standalone because I really like it. I really like the proof. Okay, until then.